You have your lab notebook? Oh, it's over there in the orange bag. You didn't pick it up yet. Yeah. Grab your guys' lab notebooks if you didn't. Maybe Emma will pass them whenever I'm thinking. Pass those out for people. And is anybody grabbing Courtney stuff? Allie? Let's put this in. Okay. All right, so the maximum, I'll go ahead and tell you, the maximum was whatever the percent magnesium sulfate was in that original sample. I think it was like 48.8%, maybe 50%, so your axis should not go further than that. So if you want to jot a note down or put it on a sticky note, your maximum for your magnesium sulfate, I think was like 48.84 or something like 50-ish%. Because magnesium sulfate have to hydrate was about 50% magnesium sulfate and about 50% water. So you couldn't have more than that anyway. So I think what we did, we didn't account for the percent magnesium sulfate in the hydrated version of it. So I'll kind of walk back to that at another point in time, but I know that you're going to see that it's not graded because I need to regrade it because that graph was horrible. Some of y'all's graphs never even gave you a chance to have a calibration curve. Because the beauty of a graph, the graph that you could have had here was implementing something like, so this was the percent control the density, yeah, percent control the density. So your graph should have been a direct relationship, fairly linear, so your dots may have been like this, you know, but as you correlate, do a linear regression, you have this great correlation curve, or calibration curve. So because the calibration curve, as you'll notice, is not a curve, right? But it does serve some use. So if I was like, oh guys, tell me the density of an 18% solution, you go to wherever it says 18% on your graph, though you never even made that solution, you could go up to the curve and go, oh, here it is, dot, 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 it's 1.11 grams per milliliter. So the calibration curve is useful because it gives you some predictive abilities. Does that make sense? Are you with me? Because some people are like in the background not with me, so just making sure. And then, oh, that first lab, so I made all these notes because I don't forget to tell you these little things. When I gave you that first lab back, half you guys fixed it and half you guys didn't. So I tried to do a quick grade of that first lab so you could understand how AP labs were graded to the level of detail and units, conclusions and stuff like that. And I did that because I wanted you to not have a bad grade because the expectations weren't clear. So if I give it back to you, fix it, and then when I regrade it, you're good. Some of you guys never even fixed it, so I tried to make sure I gave feedback this time again, but it's in a different color, as you might see. So minimum expectation is completeness. So as you're going through your labs, and maybe I'm like, oh guys, you know, Levi's got work tonight. I said labs due tomorrow. All you gotta do is say, listen, I'm gonna be up till 2 a.m. if I get this lab done. I'll push the lab due date back. I really don't mind. I usually can't grade labs in the day anyway. It's going to take me a weekend because I get like, it takes me a very long time. So if I need to push the due date back, just let me know. I'd rather them be complete than incomplete when I grade them because it's really easy to complete them if you have the time. But if you don't have the time, you just got to let me know. Does that make sense? Just really be vocal. If it's something I absolutely can't push back, I'll let you know. But usually I'm pretty clear that I'm flexible in due dates. Oh, and completeness includes your procedure. I know it's going to look like a scrapbook by the end of this, because we're going to have like tables taped in there and procedures taped in there, and you're going to you guys are starting to fold things, and I'm going to have to fold it out. It's like an interactive notebook. But take your procedures in there, or abbreviate the procedure in like 4 simple sentences. If there are 4 parts to the lab, abbreviate it. Don't give me super detailed notes, because you can always refer back to your print version. Data tables, keep them organized kind of for me. I'm not saying they have to be pristine, but I need to know what I'm looking at. So if you need to label it more, leave some space between there, like data table 1, data table 2. It helps with you trying to understand what you're working with and me as well. Error analysis. Some of you guys, so usually the first unit is a learning process, right? So the first error analysis really that you could truly do was on that hydrogen carbonate lab, because you had 3 different methods of finding the metal. You had 3 different values, and you had the true value of sodium, 22.99 grams per mole. Remember, molar mass is not grams, it's grams per mole, and I've tried to fix that on numerous of yours, so you may be flipping to that page. So whenever I look for error analysis, I look for percent error, and that's always calculated, always, if you have a value. If you have a true value, you have your experimental, okay, so always. And directional error means that, let's say I think Finky, you had pretty detailed on yours, but I made some notes on there too. Let's say y'all's group had your third trial and it was too low. Well, why was the value 17 grams per mole versus the true molar mass being 23-ish grams per mole? So if you guys got 17 grams per mole, your job is to tell me how did you achieve that value that was too low? Well, you know how to backtrack. Let's say a lot of you guys identified, oh, I overshot, right? Overshooting means you've added too much titrant, right? For the color change to occur. So if you add too much titrant, I'm going to try to write down my thoughts as I go. So overshoot, that means that when you calculate your V, so molarity times volume to give you moles, right? This was moles of the acid used in that titration. When you do that, that means that you ended up having too many or too much HCl you added. Well, then you correlated the moles of HCl to what? It's the third one with the titration. You correlated your moles of HCl to anybody? So your moles of the powder, the unknown metal hydrogen carbonate. So if you had too much HCl added and you did your mole-to-mole ratio, that's going to assume that you have more moles of the MHCO3 than you truly do. So in your calculation of molar mass, where did you put moles of metal hydrogen carbonate? You calculate your molar mass. Because that's just moles, straight up moles. How did you calculate molar mass of your MHCO3? Look back at your notebooks.
Oh, do you divide them by the difference?
Yes, so you in your calculation of using your data, you're like, okay, I got my moles of MHCO3. Then you took your grams of your MHCO3 that you started with, and you divide it by the moles of MHCO3 that you just calculated, right? Everybody with me here? So what happens to the molar mass, calculation-wise, when I divide by a number that's bigger than it should be? So this moles is down here. What happens when I divide by a bigger number? The molar mass gets smaller, right? Okay, so you're like, all right, molar mass is smaller than it should be. And this is my thought process, not you would have to write down every single thing here, but give me a good flow, okay? So smaller molar mass than it should be. Well, then what did you do next to get just the metal? This was the molar mass of MHCO3. You subtracted what, like 61 grams per mole, which was HCO3, and you got just the molar mass of the metal. Molar mass of the metal. So, guys, if you end up looking like you've had more moles to begin with, and then you divide by more moles, your molar mass is smaller. So how does it explain your sodium molar mass being lower than it should be? Because you titrated too much. You overshot. So basically, you can find if your value is too high or too low, which you can do with percent error. You can connect it to a point in the lab, which isn't a mistake by any means. It's just a process. Like a lot of the errors are going to be powder adhering to a weigh boat. You weighed out 2 grams. You added it to your beaker. Truly, you probably added less than 2 grams because some of that stuff just naturally sticks to the weigh boat. Overshooting, diluting or not priming correctly. Heating too much and more than just water vapor and carbon dioxide coming out of your sample. Like some of that powder's already getting carried away, and that's maybe how you got a different mass than you should have. So we're going to work with this a lot more, but that's what I mean by error analysis, like to the detail of like directional, using the direction of your error. Does that make sense? Yeah, it's gonna take some time, but this is like really big on the AP exam. They will basically ask you why is there error, how is there error, related calculation-wise back to your steps. So that's why I want to start doing that as soon as we can. Oh, and then in your conclusions, there you guys got that little sheet, that helpful sheet of like how to do a lab. Remember that you take this and go from your lab notebook? Yeah. Some of you guys don't have it in your lab notebook, but some of you guys have it elsewhere. That conclusion piece it's not like, oh, Levi and I worked well together in the lab. I want to be lab partners forever. Okay, it's going to be more related to concepts covered in that lab, or connecting your error analysis to concepts that you cover in the lab. So don't put a lot of I and we and us and we're awesome in there. You can do a little quick reflection on your level of group work, but I want you to keep it as chemistry related as you can. Okay? So I try to be pretty easy on grading some of those. Really, the thing that messed up most of us were exclusion of units or incomplete. There wasn't a whole lot else that you did wrong, and I, of course, trying to be flexible. All right, any questions on the lab notebooks? Okay. All right. Oh, on your desk, have your active reading guide. If you wrote in your book, that's absolutely fine. Have your active reading guide and your orgo. I'm going to draw a structure on the board, and I want you guys to tell me what it is, and then we're going to move on. Okay? So I'm drawing a structure on the board. And these are all H's. I'm just lazy. I don't want all the H's. Think about it. Raise your hand when you got it. Alvin?
2, 3, dimethyl.
2, 3. Sorry, dimethyl. So tell me what was your thought process?
A little longer string, so.
Okay, so did you count from left to right or right to left? Well, as you're starting to move on to your next explanation, how did you count? Because you counted 1, 2, 3, 4, 5. Why did you count from here to here versus here to here?
Because 2 and 3 is smaller than 3 and 4.
Right. So the substituents that are attached to the main carbon chain, which happens to be this one, they are lower in number, so they're prioritized. You could have also counted like from 1, 2, 3, 4, 5. Really, because that is a substituent if you count it this way instead. But they end up being the same. Yeah.
If you were just thinking 1, 2, 3 dimethyl thing, then how do you know which way the person counts?
It doesn't matter. You're drawing it yourself as long as it's correct. As long as it's correct left, right, or right to whichever other way, then that'll work. Because it's, basically the way the way everyone is going to count it is lower, keeping the substituents with the lowest carbons. It will work out. Okay. All right. So and then it's pent because there's 5 carbons, and then it's 2, 3 because those are the carbons that the 2 methyl groups are on, and you have to say dimethyl because it matches up with having 2 methyl groups. What if I've done this instead? And I'm just going to adjust it from here. So that's a 2 and then CH3. How will that change the name? Do I? It looks like I've just added an ethyl group, right? The carbon chain is longer. All right, what's the name of, or what's the carbon chain length here? So 1, 2, 3, 4, 5, 6, or 1, 2, 3, 4, 5, 6? The first way or the second way?
The one where you count 6.
I mean, I know it's 6 and 6, but which way is going to keep the substituent that's here lower? Okay, so putting 1, 2, 3, 4, 5, 6. Why?
That way the substituents will have the lowest number.
Right, so the carbon chain being this means that's the substituent, so what's the name of it? I know it's hexane, give me the full name. Three, 4. I'm sorry, I meant comma. But I got you. So 3, 4 what? 3, 1, 2, 3, 4. Yeah, okay. Say again. Di, right? Dimethyl hexane. Right? So basically, we took, I wanted you guys to count from 1, 2, 3, 4, 5, 6, but you could have done 1, 2, 3, because that would have been the 3, the methyl on the 3, and this would have been the methyl on the 4. It would not have mattered. Yeah, thank you. This one? Because I'm not counting as my main chain. Yeah. Because it goes 1, 2, 3, 4, 5, 6. This is a separate entity. It's not included in the chain. It's because it's got carbon with an H and H and H here. I'm drawing on top of 3 structures at this point. Sorry. Yeah.
Maybe you're counting out like which direction you're using. Like if you had a double bond.
You prioritize the double bond. You would prioritize the double bond
But
first.
do you have to count the, I was gonna say, do you have to count the same way? Well, like, if your double bond was after like the first carbon, would you have to go from left to right the whole time? Like, if you were counting for how far your knuckles in?
If your double bond was here instead, that would change this to be, okay, so first of all, that would be 1 hexene, right? So that's that first, the bonds in the first carbon, and that would be 1, 2, 3, actually would be the same thing, 3, 4, right? 1, 2, 3, 4, dimethyl 1 hexene. Yeah. All right, so you guys are like big boys now. Got some organic chemistry under your belt. But we'll kind of do like just do a quick one, warm up every day, just kind of keep you in tune. But the next one you're gonna see who's actually started the second video. It's okay if you haven't. You'll see some like chloro and bromo. Can you imagine what those are? Chlorine and bromine substituents, and it'll get a little bit more complex with using more functional groups like alkanes. Aldehydes, ketones, carboxylic acids. So carboxylic acid is something we already know. If I said to name this, to name that, can you name that? Don't get crazy with it. Look for the formula that you know and that you've seen for a year or two of your life at this point. How many carbons are here?
2.
Okay, how many hydrogens?
4.
4, but there are 2 types of hydrogens. These are on a normal carbon. This is on an oxygen. So I'm going to label this C2H3O2, and then this H is an acidic hydrogen because it can pop off to make protons. Acetic acid. That is acetic acid. And you've seen that, but now what we're going to start to see is like, why the heck is this thing an acid? Well, because it has this wonderful hydrogen that's really no one cares about, because the oxygen's like, man, if you just go away, I could take your electrons. I'm electronegative. And this one's like, yeah, then the electrons be closer to me. So then they basically allow for that separation to exist, leaving the hydrogen free to leave, which makes it a proton donor, bad acid, bronzed acids are donors, so they leave. We call this entire group right here a carboxylic acid. And that's the reason it's an acid, because the H is able to leave. You'll see that in the next video though. Okay, so it's okay if you have some functional groups already under your belt too. Okay, I am quickly going to go over some of the content review from, oh, hold on, guys, I came up with a project. Okay, so I've got so many things to tell you guys. So the project that's going to allow us to go to the beach, okay?
Okay.
Calm down, calm down. So basically, I had to come up with this idea that I could wrap in as much as I could of environmental chemistry, biochemistry, climate change chemistry, etc. So I came up with a project called Global Chemistry Crisis Project. It is not due until January, but that does not mean you will not start looking at it now. So I'll go ahead and show you what this looks like. So I've got this nice infographic for you to see that this does relate to environment, the, ocean acidification in general. So what your responsibilities are, I already have this open, but I want to open it again. So I'm leaving this up, so, oh, that's the wrong one. Whoops. Is this the right one? Yeah. Okay. So I came up with this so that I would have some support from the people who have to approve this. So purpose, expose you to real life chemistry, through real life problem solving. What is the crisis? It's ocean acidification. People, have you heard of this crisis? Okay, it's bad. You will start to evolve your knowledge about that as we go. So as we learn about this, we're going to come up with an engaging way to inform our school community about the issue, the science behind it, and then of course how we can solve the issue. You will design as a whole entire class. This is a class-wide project. Okay, you've probably never had a 17-person project. 18 including me. I have a collaborator at UNC Charlotte, now 2 of them. One's a environmental chemist and one's a biology professor. So I've got 2 outside of the school community members involved, and so we're gonna make this happen. So we're gonna design an informative, academically advanced, and an engaging way to share about our ideas and share about our research. Here are the minimum requirements. Describe chemistry concepts. You'll notice that I have things that we know now, a little bit of organic, thermochemistry, which is like in November, Collated properties, which actually is not till March, so we'll kind of keep adding this as we go. Oxidation reduction, that's our next unit. Gaseous chemistry, unit after that. Equilibrium, our month-long unit. So we're going to have some things that are not, we don't even know yet, and that's totally fine. The other requirements are talking about humans' roles, which if you took an AP Human Geo, or if you took in apes, then you'll be able to add to that a little bit on that side, which might be your specialty. Like if you took that, you would claim that part of the project. What can humans do to alter it? Professional interviews. If I need to bring people here, I'll bring them here. I'll have them meet us after school. But we will include them in our discussion because they'll be able to open the door a little bit further for us. What will the project include? Minimum, some images, nanoscale, macroscale, chemical equations, atmospheric and oceanic interactions, measurements with molarities. I'm talking about molarities today. Calculations in parts per million. I might get to talk about that today. Calculations with pH, that's later in this unit. So some of the stuff is really relevant now, so it's going to be much more relevant later. And of course, as you find out more things that you'd like to include, we can do that. So this is the part I need you to participate in most specifically. You will start to self-assign parts of this content. Maybe it's you find images, maybe you find infographics just to start with to give us some good ideas. You're going to start self-assigning and group assigning things that you would like to take part in on this big, huge project. And so as you go, you're going to document. So Levi, what struck your interest so far? Everything. So he's going to do the whole project, guys. He just volunteered. Okay, so you guys are going to think about something that struck your interest, and you're going to start tackling some of these. But if you want to say, you know, Savannah and Lucas are going to do these two things together, I need to know that. If you'd like to work with somebody consistently the entire time, claim them, and that's fine. But I just basically want to know what's in progress, what the dates that you're starting, and then what's going to be coming next, and like, you know, giving yourself deadlines. Like, okay, I'm going to have my part done by the end of November. Something like that, and that's fine. If you need to set your own deadlines, I'm leaving that up to you. I'm really a facilitator here. But to get you started, I did find quite a number of resources to get you started. So I'm going to leave that for you to look at. And then I found this, okay, basically I just Googled climate change infographics, and that's about it. That's the Google link to that. You guys can see it's huge. And then, of course, if you find other resources, you can add them to our list. Right now, we're just in, like, information collection phase. That's it. I don't want anything done on this week. I don't. But if you want to, that's up to you. But as you start to, if you know, like, oh man, I'm really interested in the human impact, you might want to go ahead and claim it. That way I don't have anybody duplicating or triplicating what you are doing. Does that make sense? So this is not due till next semester, but this is going to kind of whittle us into our marine chemistry trip. Okay, and I do have a collaborator, Yancy Shaw, that's going to go with us because she said she could do some oyster dissections or some crab dissections with us, and we could like maybe learn about something else with that. There'll be a lot of interdisciplinary stuff that happening here. Like, I'm so excited. Okay, so that's our project. Woo! You guys don't seem nearly as excited as I am. Thank you. Thank you. Okay. Yeah, I know you're tired. So what time we get out of here?
7.
Huh? 10:07. Okay, I'm gonna do two things. You guys have the paper that looks like this. It's just a note sheet. You just got it? Allie, will you grab a copy for me too? So, I know you did a good job of reading over your active reading guide. I know you did. I mean, participating in it, I need to see those, but just not yet. I'm going to walk through some of the basic information I need to, and then my goal is to help go ahead and have us do a solution preparation using a specific molarity and from powder to solution. That was my goal today. And as we go through this, please let me know if you're like, we got it in low, move on. I need some vocalization here so that I know that I'm not over explaining things that you already understand. So this is my slide. You guys have yours. I try to give you the basics here. So who knows a lot about water? So the characteristics, we know it's polar. What part is the negatively charged area? Oxygen. Why?
Because it has all the electrons.
It does have electrons, and it's highly electronegative, meaning it has a strong pull for electrons. So as you're starting to realize, I'm going to start having them draw them out as molecules or particulate matter diagrams, even to the point where we're having the partial positives and partial negatives on here. So this is a partial positive. Have you ever seen that symbol like this? It's like a lazy, I didn't want to finish the 8, and then a plus. Partial positive, partial negative. All right, so the only reason water is a great solvent is because it can do this. It has this property of polarity. So it has the ability to take its positive charge on its hydrogen, or its hydrogens, and point it towards something that's negative. And on the other side, okay, so Emma, come get a fill of water. Stand up, stand up. Get a fill of water molecule. Okay, so you guys are ionic salt. Participate. Gosh, I know, I have to like really focus on participating. Okay, so you're an ionic bond. Stay together. All right, Emma, go on that side. Go, just scooch around that way. All right, so she's the positive one. She's the negative one. She's a salt. You guys are salt, okay? We're not going to salt you, but wait. So you are water. You are the positive hydrogens, right? If she's the negative one, you're just going to attract, right? Okay, so I'm the positive one. I'm sorry, she's the positive ion. What side of water will attract the positive ion? Okay, so now attract. I'm just going to type with my right. Okay, then we'll right. That's it. That's the only thing. Water is great at doing that. We just associate it with salt. Boom. Okay, but not everything can do that. If I was a non-polar solvent, salt would be like, can't touch me, because there's no attraction. There's nothing there to do that. Thank you, Emma, for being my water. So that's why water is great at dissolving things, mainly things that are polar or ionic. Now, when I say dissolve, that does not mean what you think it means. Dissolve and dissociate are two totally different terms. So I like to use the word dissolve at first, because it's something you're familiar with. But the word, the fact that it's dissolving things that are polar or ionic is very specific, because it can only attract things that have a partial charge to them. It cannot do much to something non-polar. Thumbs up if that makes sense. Because it can't attract, it can't really do any kind of damage to anything non-polar. So the whole polar thing does include an alcohol, which is like, I don't have a picture of one up here. I think I do on the bottom. It does include something that is like this. Is that an alcohol here? Yeah. So this is, that's ethanol. That's alcohol. That's what yeast make when they do fermentation. So this OH group here, if it weren't there, that whole entire thing would be nonpolar, correct? No differences in charges anywhere. But this thing right here is like, oh man, we got this partial negative and partial positive, meaning water's like, aha, we can attack. So this right here, this water molecule does orient itself to attract the H to the O because of the opposites in nature do attract. Now this little dash line right here, what is that called? Do not say this. What is this dash line right here? What's that attraction called? Hydrogen bond. Do you see that you said bond? Do you mean bond? No. I really want to rename the entire thing and call this a hydrogen attraction, but I don't have that kind of power. Okay, so hydrogen bond is what we call this dash line, or working in dungeon, but hydrogen bond is what it is. It's not a true bond, it's just an attraction. So we're going to get into IMFs and intermolecular forces later. Okay, so I want you to draw something. Draw a hydrogen bond. You may have drawn what I did, but why don't you draw something else? You need something to write with? Oh, I'll give you something to write with. What you got? Did you draw something? It's not really an art group. It's a molecule and another molecule getting near each other. Can you draw two molecules? It has bonds in it. Okay. Does anybody have something specific they can share? Go for it, Vinky. Okay. So circle molecule, two hydrogens where? Okay. Okay. And? No. Hold on. I'm glad I'm stopping here just because. So when you draw a hydrogen bond, you need two things. You need water generally and something that it can attract to. Just something by itself is just straight up a molecule, not a hydrogen bond. So these two hydrogens, I'm just going to go ahead and call this water, H2O, and I'm going to allow that to attract to something else, because you absolutely have to have another molecule or another atom or another something involved. If not, it will never be a hydrogen bond. So I've drawn what here? NH3. Name. Ammonia, okay? So ammonia has 2 dots up there, meaning there are 2 one a pair of electrons. Water has 2 Mickey Mouse ears of their electrons. Where would this attract on my ammonia? Would it attract to the nitrogen or to the hydrogens? The hydrogens, because this is a partial negative, and these guys have partial positives because this up here has a partial negative. So yeah, this partial negative here would attract to that H, or maybe even this H2, just depends on how they're oriented. But the hydrogen bond is literally this part right here. It's not really a bond, it's an attraction. It's not something in particular, it's the force of attraction, that's all it is. You will have to draw a hydrogen bond, I almost guarantee you, on that AP Chem test and on my test. They've had a similar question like this many, many times. So again, NH3 and another NH3, they can attract to each other by this dash, 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 which is a hydrogen bond. And then same thing with water, they can attract by dash, dash, dash with ammonia. So that's how medicine works. That's how medicine dissolves in your body. Who's taking medicine and you're like, oh, I gotta wait for 8 to 10 hours to take another one. Basically, you're waiting for the water or other solvents in your body to start to attract it, or pull it into solution so it can enter your cells. Sometimes that takes a long time. Okay, so that term I mentioned earlier, I said dissolve. Most people are like, oh, we know what dissolve means. But I want you to figure out how does it differ from dissociate. So the key point is that dissociate or dissociation means to break something apart. So Emma and I teamed up on Chloe and Avery, and we made them dissociate. We made their ionic bond cease to exist, so we break them apart. And so the way water can do that is because it has that polarity to it. It cannot do that to anything that is non-polar. It can only do it to things that are polar or salts. So you'll see that this ammonium nitrate is being dissociated into ammonium cation and nitrate anion, because water has this, I'll turn the lights off for us, has this ability to surround it. Okay, so this is, for example, sodium and chlorine. Sodium has what pointed towards it? The oxygens pointed towards it, and chlorine has the hydrogens pointed towards it. So when you have to draw a dissociation, you have to draw the water molecules in their correct orientation. If not, you don't get it right. They had an example. They basically had something like this: draw calcium chloride dissociating in water. On the AP exam last year, particulate diagrams is how I call those, so that you understand with the particulate, like smallest level possible, to start talking about how they are orienting themselves. Okay. Oh, and this is just a bigger picture of that. You guys will be drawing particulate matter diagrams quite a bit this unit. So this is a lattice of sodium chloride. You can see that water is now being added to it, and then you can also see how they're orienting themselves. So I give you ionics and polar things as a good example of dissociation. What about dissolve? What is that going to refer to? Go for it.
It doesn't ionize it, like the ions don't break off the water molecule, just kind of surround it.
Surround it. Basically, they gang up on it and they surround it. So the picture I have that would explain that is here. So this is sucrose over here. This was the picture from your book. So the sucrose molecule is this one right here and this one right here. You'll notice they're not breaking apart. Water is simply surrounding it and hydrating it to make it look like it dissolved, right? Because you put a tablespoon of sugar in coffee or sweet tea, there's not just particles just hanging out in the bottom like a big massive solid, right? Every single teeny particle with the molecules in it starts to fall apart some as the water surrounds it, and so that it tastes sweet to you. There's no empty powder or a solid at the bottom. They're in suspension, but they never ionize. We use the word dissolve to say that, whereas things that are, the water molecules are surrounding that ion and that ion, we use dissociate to represent that. Now, Levi said ionization or ionize. He I'm good with ionized to describe this because that's truly what's happening. But the term ionized is actually used more for acids. So let me just make sure we got that. We got that. Covalent compounds are nonpolar generally, so they're going to be dissolved, not dissociated. Okay, so the term ionized is actually usually reserved for acids or molecular compounds that do not form charges. Generally, they don't form charges, generally. But if you think of acids, these are ones that we've generally been exposed to. We know to make the formula, we have to crisscross charges. But not all the time are they considered ionic. Generally, they're not considered ionic. So a good example of this would be, what would you name this? Cyanic acid. Good, I've almost said hydrogen cyanide. So cyanic acid is going to have a double-headed arrow of H plus and CN minus. And I'm going to tell you why this double-headed arrow exists here. It's because it's a weak acid. And it does not do that fully. It does not ionize, it does not ionize fully. So it's got like 1% ionization. Something, I mean, I'm making it 1%, it might be 5%, but it's something really, really low. And I'm gonna cut one of the lights on so I can't see y'all's faces. So tell me if you're okay or not. All lights on? Yes, you can still see that, yeah. I'm probably gonna say we're not gonna get into that loud today, and that's okay. I'd rather get through content. But tell me if you're getting sleepy. Yes, stand up if you need to stand up. I got a little bit to talk about for today. Okay, so another way that this ionization, I know I'm sleepy too. I was up too late making that darn project. I was really excited. My husband was like, just go to bed. I was like, no, I'm going to tell them about this tomorrow. So another way that we can ionize things is through photoionization. So an example is ozone plus ozone can form free radicals or form ions by UV being added to it, or photons. Photons are light. Photons are light added to them, and it's going to make something like a free radical. And free radicals react with everything because they generally are lacking an electron. So it's maybe lacking an electron, or actually gains an electron. So that says plus or minus right there. Looks like chicken scratch, but that's plus or minus. But the reason that these are actually really harmful to us is because they don't care where they take electrons or gain electrons from after they become this. They take it from anything. So the way we call this process is oxidation. Many times we call it oxidation. What do you eat that counters or limits oxidation in your body? Say again? Antioxidants, right? Antioxidants. Where would you find those? And what kind of foods? Say again? Green stuff. That's probably like more folate, vitamin A, vitamin K.
Fruits, berries.
So things that have dark pigments. So berries, so think blueberries, blackberries, raspberries, anything like that generally has a lot of antioxidants in it. So we actually eat those to counter things like this. This happens all the time in the ozone layer, all the time. And we eat things to counter the natural rapid oxidation inside of our bodies and inside of our cells. It's bad inside of your cells. Okay, so we got those. We have a lot of terminology that's, as you're kind of seeing here. Terminology. Okay, more terminology. Electrolytes. Just in general, the term electrolyte means what? Ability to conduct electricity in solution. In solution. So we're talking about solutions quite a bit. So would you consider copper metal an electrolyte? No. What's the term that means it can conduct electricity as a solid? Conductor, right? It's a conductor. It has the ability to conduct electricity. As a solid is conductor, but electrolyte is in solution. So I'm comparing and contrasting a lot of words here for you. So there are some varieties of electrolytes. Some compounds, when they ionize or dissociate in water, they do so 100%. There's nothing left that was not separated. So we call those strong electrolytes. And generally, most of our salts, group 1, group 2 salts, most of those are going to be absolutely 100% dissociating in solution. Specifically, when I'm talking about solution right now, I'm talking about aqueous solutions. Later on, we'll talk about non-aqueous solutions. But as these salts dissociate, so I want you to write out the dissociation of calcium chloride? On your paper, write down calcium chloride, not in the word, in the formula, please. And I want you to write the way you would show the dissociation of it. CaCl2, and then what? Breaks down to Ca2 plus and how many? 2 chloride ions. That is a dissociation reaction. I'm not showing water, right? Because we're like, I'm telling you, I'm talking about dissociation in aqueous solution. Do not include water. You could put aqueous, and solid over there. That's fine. But right now, I just want you to know that we make more ions than we started with, right? The ratio changes from a 1 calcium chloride to 1 to 2 ratio of calcium chloride or calcium and chlorine. So a lot of the times, you're going to have a large increase in concentration of ions because you make more ions than you had to begin with. Yeah.
Do they ever dissociate diatoms?
No, it will not, because it's thinking in its ionic way. As an ion, or as an ionic compound, it breaks into ions. Ionic compounds do not break down into gases. Make sense? Okay. So we now have to memorize these. And some of you guys have this memorized from if you were in my class. You need to memorize the 6 strong acids. The 6 strong acids are called strong for one reason. It's because they dissociate 100%. They're not strong because they're like walking around real buff. Okay, they're not strong because they burn your skin. Most acids burn your skin. Most acids taste sour. Most acids have some sort of corrosive abilities to them, no matter if they're strong, weak, or we're still not sure what they are. Okay, if they are strong, it's only because they make ions 100% of the time. So HCl breaks down into what and what? Hydrogen ion and chloride ion. Same thing for all of these, but remember, do not break polyatomics apart. This nitrate stays nitrate. This perchlorate stays perchlorate. The sulfate, I'll go over an example of that one in a second. That one's different. But most of these do break down, all of them do break down 100%. The way we generally write this is that one we do show with water, because acids don't do that by themselves. They need water to do that, just like the salts do. But it's common for salts to be written like this and acids to be written with water, with the formation of what's the H3O plus called? Hydronium, with the inclusion of hydronium being a product. So, same story, different thing. Bases. Strong bases, these 8 strong bases. How do you memorize the 8 strong bases? Where is it? Okay, from a point on the periodic table over here, write this down for yourself. So, you'll notice it goes most of group 1 and group 2 bases here. So, over here you've got lithium, sodium, potassium, rubidium, cesium, and then it goes up from barium, strontium, calcium. Doesn't that look like a lowercase b? Lowercase b, there's 8 of them, lowercase b, 8 of them, and they're all in their hydroxide form. So it looks like this, kind of. All of these have to be hydroxides, and they're considered strong bases. Again, what does the strong refer to?
The ability to ionize, the ability to form ions.
100% of 100% ions. There's nothing left over that was there previously. Okay, so it's really easy. Once you know what strong means, you know what weak is. Weak means that they do not dissociate well, and so well is going to be varying. It might maybe 1% of them are actually ionized, aka dissociate. Maybe 2% of them do. Maybe 3% of them do. Maybe 10% of them do. But there's nothing close to 100% here. So they chemically are different because whereas maybe my board's been goofing all morning. So basically, chemically, these acids up here and these bases right here, they have a pretty distinct charge separation between their 2 halves, and so they break apart easily. Whereas so acetic acid, which I drew earlier, it doesn't have as distinctive charge separation, so it's like, I'll stay here for a little while. Like, you really got to rip that baby apart to pull that ion or pull the H plus off. Same thing for a base, if I can make my computer work. So we're going to pause for a minute, because I can't go anywhere. And I want you guys to look at your notes. And I want to write down on the board.
There it goes.
Oh, right. It's probably like 8 pages of extensions here. I still don't have the power. I got no power, people. Okay. So I want you to draw this on your paper for yourself. HCl, and they're 2 little circles, and they're atoms. I'm trying to draw this bigger so you can see it. And HF. I'll do HCl and HF. And they're 2 circles. If you put HCl in water, what is it going to do? Okay, so 100% of them will form H plus ions and chlorine ions. Not together. They are now separate. They have dissociated. They have separated themselves from each other. 100% of them. All right, go look at your paper. What are the other 6 strong acids? HCl, HBr, HI. Stop there. Those are the 3 that are connected to each other. HCl, HBr, HI. HF has a smaller radius, so it actually stays connected to H more so than not. Okay, so those are the 3 binary acids: hydrochloric, hydrobromic, and hydroiodic. And then sulfuric, nitric, and perchloric. Okay, so knowing that much, we know that all of those strong acids 100% ionize into 2 parts. What happens to this when you put it in water? Say again? It stays basically as it is. I don't know why I put P. It stays as is. It does not do anything. It does not dissociate. Now, I'm going to say 2% of them do dissociate. I'm just going to do as a happy face. That means dissociate for me today. But most of them do not. And so that's why on this picture here, all the HCl has separated. There's no such thing as HCl anymore, guys. It's gone. But the acetic acid, we have 1, 2, 3, 4, 5, 6, 7, 8, something like 8 that never did anything, and 1 that associated into the 2 ions. So a very low percentage of them do. All right, I accidentally skipped. No, I didn't. Okay. Okay. Let's go ahead and talk about non-electrolytes, and I'll come back up here. Non-electrolytes, they're not ions. 0%. Nothing. Okay. Sucrose, anything molecular like that, does not ionize. So but it's not that they're weak electrolytes, they're non-electrolytes. There's a distinct difference there. Good with that? Vocabulary. Okay. So the big concern is that calcium hydroxide, strontium hydroxide, and barium hydroxide, those 3 bases in group 2, generally they are very, very insoluble. You put them in water, it looks like they don't do anything. It's like just a powder sitting on the bottom. So you're right, they are very insoluble. However, the little bits of calcium hydroxide that do dissolve, they do break down 100%, meaning they dissociate 100%. So we still call calcium hydroxide a strong acid because it does what? Dissociates 100%. But it's an insoluble one, meaning not all of it dissolves. So basically, if not all of it dissolves, that's fine. But all of that does dissolve, does dissociate, if that's 100%, then it's good. All right, get up and stretch for a minute. You guys are sleeping on me. Get up and stretch for a minute. And I'll decide. No, we gotta go today. I was gonna say I'll decide, but I gotta do like 2 or 3 more slides after this, and I'm gonna stop. I have candy. Candy? I even got old lady candy. Butterscotches. And a half whole thing. Strawberry. I really do try to increase your brain power. You don't want it.
That's like sketchy Halloween.
I will be that person that hands out butterscotch and Halloween. Here.
Take that from the one. Try to get rid of all your Halloween candy so you don't have to sit on the front porch all night.
No, I just like fun candy. Okay, come back up here. I'm going to try to do this in my jeans. I don't know if I can do this. Let's get a good deep breath here. Stand up, stand up. I got 20 minutes left and I need this.
Are we doing yoga?
We're gonna do at least do the tree. So you can't so we can do the tree. I need a good solid, you need to do a half tree. Do not put your foot on your knee. Either below your knee or above your knee. No on your knees because then you'll block your knee out. So balance, balance, balance. Core strength. Up. 4, 3, 4. Count for the deep breath, sorry. I have to jeans on the scalp. Okay, back. Alright, mommy can do that together. Let's go back to Jordan. Okay, it's been crazy exercise. Alright, so on the very lower side, my boys in the back, thank you. Lower right hand corner, you have this on your sheet. I already have shown you that each of these ionize 100%, yes? Now the sulfuric acid is the only one that does not act normally, and that's because what's the word that says I have 2 protons? Acid when it has 2 protons. 2 H pluses. What's diprotic? Diprotic. Okay. So protic di means 2. Protic means proton. Why is an H plus called a proton? It's just a proton. There's new neutron, and the only electron it had has been taken away. So commonly we call an H plus a proton because it's just simply a proton. Okay, so the diprotic acid H2SO4, it does 100% make 1 H plus and a HSO4. What's this called? Bisulfate. Okay, it does 100% do this. That's the only strong acid that can do this and then be considered a weak acid in the next step. So this guy still has an H plus, yeah? Is it one of the big 6? No. Double arrow. H plus and SO4 2 minus because it lost its other H plus. So this is considered 100% ionization or dissociation. Sorry, I'm going to keep saying ionization. I mean dissociation. No, this is not ionization. And then the second one is considered weak because it does not have the ability to do so 100%. Ionization. Acids, you say ionization. Salts, you say dissociation. Yeah.
Is there a yellow arrow because it like fluctuates, like it ionizes so back?
Yeah, it's like it ionizes, and then if you affect its equilibrium, it shifts back. And so this one will never, ever, 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 ever do that. It's like once it's gone, it's gone. Okay, so the bases, I think all the H's are the hydrogens are, the acids are really self-explanatory. The only thing is to note is that if it's from the big 6, it's not strong. Everything else is weak. Any other acid is weak. Strong bases, like I said earlier, they do dissociate into their 2 ions. I'm going to try my best to stick to these 2 last bullets of rules. So what we're going to start doing tomorrow is writing net ionic equations, NIEs, net ionic equations. So we need to know when to write them as ions and when not to write them as ions. I'm going to try my best to stick to those. So circle those, put a big heart next to it or something. We'll try to stick to those as we go. I'll explain within an example though, because it doesn't make sense by itself. So what will you never, ever, ever, ever ionize? For example, in a net ionic equation, you will never ionize things that are gases because they're not able to be ionized. You will never ionize things that are precipitates, meaning that they are insoluble products, because they can't dissolve to ionize. So if they never dissolve, there's no way in Hades you're going to get it to ionize. And gases, they don't really dissolve either, so you can't ionize them. Weak acids and weak bases, how do you know if they're weak? They're not in the 6 strong or the 8 strong, right? You cannot ionize them significantly, so we don't even attempt it, because it's only 1%, 2% kind of deal. Metals, they're solids, right? We're not going to ionize those either. The only thing to make sure is like when are you running a metallic ion, and when are you just writing a metal. So when you write Ag plus versus Ag, that is different than that. That is an ion, that is not. So just make sure you're really strategically using your charges. And yeah, non-metallic elements like carbon is not an ion, it's just like graphite, solid. Diatomics cannot be ionized, they're gases, they're molecules. And sulfur, which you might see as S or S8, it is also not able to ionize. So these are the rules for ionization. When can we not and when can we ionize things? Okay, last thing, and then we're going to move to molarity. Calculation of molarity. So we went over this within the context of a lab, right? We did a little teeny bit of this. Can you at least highlight this or write this down? Because that's going to be your best friend for a while. And I'm going to give you guys about 5 minutes to try to solve that problem, and then we're going to move to the next page. There's 2 of them, or 3 questions here. Levi, get me started. What are we doing? Okay. So, why? Okay, so you're going to use the molar mass to get to moles. So basically, the first thing you're looking at is the question. The question is asking for molarity. Well, if the question is asking for molarity, which is capital M is different than lowercase m. Do not put lowercase m. That's molality, which is next year. Okay, we're not touching it until next year. Molarity is moles of solute, which is the calcium chloride in this case, over liters of solution, which is the whole shebang, right? Liters of water. So you're telling me to take 38.6 grams of calcium chloride. Look at me putting on my labels and everything. Grams, units, what's the molar mass of that? 110? 1 mole of calcium chloride is 110.9 grams per mole, okay? Gosh, 98. I'm a mess today. Grams calcium chloride. Okay, so we got our moles, and then what? How do you get molarity? Okay, instead of stopping and going, okay guys, I got my moles, look at my moles, I'm just going to go ahead and multiply by the reciprocal. Is that okay? Same thing. So I got moles, right, because grams have canceled. And if I make my next step as a division, so I'm dividing by this in liters, right? So 0.4750 liters. Put a 1 up there, that's basically dividing, yes? Math. All right, so moles divided by liters is molarity. What's that molarity? Wait, what? Savannah, what'd you say? 0.732. Anybody else? Okay, yeah, so we got some consistency here. How many sig figs should I include here? Why 3? This up here gives me my 3 sig figs. This one up here gives me 4. Stick with the 3 because that's your limiting. So this is right. Yay! All right, who remembered mostly how to do that? Give me like a little handshake. Okay. Let's do 1 or 2 more. So these are different, right? What am I solving for here? Volume, not necessarily V1, but volume in general, right? And now I'm solving for moles. So earlier was just simple division. Now I'm going to manipulate the molarity given to me, make it a conversion factor, and solve appropriately. So, question, what is the volume of that molarity ammonium chloride that contains 2.5 grams of solute? So I have got the question of volume. I have 3.67 molar given to me, and I have 2.5 grams of aluminum chloride to begin with. Which of these values do I start with? Problem solving. Say again? I have to start with my grams, right? Because my molarity, remember, molarity is not a unit. It is actually 2 units. It is a conversion factor. So I'm just helping you through problem solving. So start with your 2.5 grams, and what do you have to do with this? Okay. Aluminum 27 plus 152, what is it? 150? I believe the 130 something, sorry. So 1 mole of aluminum chloride is what? 33. Okay? So aluminum chloride cancel, right? Oops, I didn't even cancel that 33. That's still there. I thought I wrote aluminum chloride there. Alright, so now I'm in moles of aluminum chloride. Get me to volume. What's next?
Molar mass over.
I think Arushi's got me here. So,
Oh, it's 1 liter over 2.6.
so you're taking the molarity rate and you're flipping it upside down. So don't forget that this is actually 3.67 moles per 1 liter, right? So if I take that and I flip it, 1 liter goes on top, 3.67 moles goes on bottom. My moles and moles have to cancel. I got it here, right? So my moles of aluminum chloride, moles of aluminum chloride cancel. Now I'm in liters. I'm in a version of volume. I'm good to go. So we just used our molarity as a conversion factor. That's the point of doing that one in that manner. So I'm trying to keep it with stoichiometry versus like proportions. Stoichiometry. So
Very small.
yes. How many sig figs should that be reported to? 2 sig figs. Okay. Next one.
Wait, do you have to like keep it? Can you keep it in liters, or do you have to like change it?
If I ask more specifically, it would be specific, but I'm just going with liters for now. Okay. How many moles of ammonium ions are in this many milliliters of this molarity ammonium sulfide? This one's got one extra step that we haven't had to consider yet. So what's our question? So moles of what?
H4 plus.
NH4 plus, good, are contained in 35.6 milliliters of 0.639 molar. What's ammonium sulfide?
NH4 plus. That's 2.
Okay, but how do I write that?
Oh no, it's NH4 plus 2.
2S, right? Sulfide crosses its 2 down. Ammonium 1 crosses 1 over. So we have this now, right? So I want you to realize that we have 2 ammoniums in a single ammonium sulfide. We're going to use that internal mole ratio later here. What do I start with? Milliliters. So I'm trying to give you a chance to think about once you see a problem, how do I get started? So you have your milliliters. I can't do squat with milliliters. Change it to liters. So you could do millimoles over milliliters, but I'm going to go with liters for now. 1 liter has 1,000 milliliters in it. Okay. Now what? How do I use my molarity? As is or flip it? As is, because this is moles per liter. I need moles per liter at this point. So 0.639 moles of ammonium, that's 2 sulfide, in 1 liter of that solution. Okay, so milliliters cancel, liters cancel. Now I'm in moles of ammonium sulfide. Next, what's my internal mole ratio? 2 to 1. So there's 2 moles of ammonium in 1 mole of ammonium sulfide. How many sig figs? 3. So remember, metric system, don't consider their sig figs because they will always limit you to 1. They are not a measurement. They are used for your purpose of conversions. This internal mole ratio, again, is not a measurement either. It's a count. Counting is different than measuring. This is like 2, not 2 grams or something. We just have to implement this from its subscript. So don't use that as a sig figs. You show 3 sig figs and it's not a problem. And it's not an answer. So I know I can show you the dilution equation, but we did the dilution equation in the lab last minute. So pull out the packet that says molarity problem set. It's I think I even have page numbers on it this time, guys. Page 1. It's got a big 1 next to it. It's on 4-2 page. So you have this front and back. You gotta stay organized. I only made like 1 extra copy. Do not lose your stuff. So I'm gonna tell you guys which ones to do. Actually, guys, read through 1 through 10 and tell me which ones you don't know how to do before I tell you which ones to do. Look at 1 through 10. Okay, actually, for sure, I want you to circle number 4. So you're doing 4. generally you should know how to do all of these. But do number 4 right now. We're going to go to number 4 right now. So now Alvin, tell me your thought process. Number 4. Maybe. What's the question here? It says concentration, right? What's that asking for? Well, what it's saying concentration, what is that? What value does that mean it's looking for? Molarity, right? We have molarity. It's asking for molarity, right? So you're like, how do I do this? You need to think about the ratio of ions present. No conversion is necessary. Think about your ions. So you have aluminum chloride, right? How does it dissociate? Into what? Aluminum 3+, so you're talking ions to me, and how many? 3 chloride ions, okay? So if I start off with a 0.250 molar solution of this guy, knowing it makes a 1-to-1 ratio of this one, what's the molarity of aluminum ion? 0.25. Since this is a 1-to-3 ratio, what's the concentration of the chloride ion in solution? 0.75. Right. So that's all it is. Remembering that when you ionize or when you dissociate, generally your concentration of ions definitely goes up because you're making multiple ions. And then you also sometimes need to actually know the actual concentration of those ions based on their mole ratios. That's all number 4 is. It's just a little different. All right, so I'm going to leave that problem set up to your purposes for optional work. If you would like to practice, you have the answer key there below. But you need to practice if you're not comfortable with molarity. Last thing, and then I'll leave you alone. How do you make a specific concentration? How do you make a specific, you have 2 different things you start with. Whenever you're making a concentration, you're making a solution. You start with a solid. How do you make a solution? Add water, or no, you should add water. Because generally if you add it to water, it gets stuck on the sides of the volumetric flask you have to use. So generally you'll add water to it. Or I can give you a stock solution like I did in the blue Kool-Aid or Powerade lab, and you have to take that stock concentration and dilute it to another concentration. That's using the molarity dilution equation M1 V1 equals M2 V2. So I'm going to show you the equipment associated with this. Do I have this on your paper? No? Okay. I want to show you the equipment that is required for this. In just a second. Here it is. Okay, I'm going to cut the lights on. So do you recognize any given equipment on the board?
Yeah.
Okay. If you want to take a picture of this or write it down, by all means, absolutely do it. I'm going to use the pointer so I can get out of this picture. Where's my pointer? Okay. So the first piece of equipment you should identify is this one. This is a volumetric flask. Who's ever used a volumetric flask? It is not an Erlenmeyer flask. Erlenmeyer flasks have that kind of triangle shape to them. The volumetric flasks are more expensive because there's an etched line. Do you see the etched line right there? That right there is so super duper accurate and precise and correct, and every possible thing known to man that's correct. That is so absolutely correct. These things sometimes run hundreds of dollars because they are so accurate. And a lot of research labs use them, but we'll use them for making our own solutions many times as well. So the volumetric flask is what you're going to be adding your solute to. Solute is going to be generally in a powder form. You add it to here, then you'll add water, usually like about halfway, about as actually the term I like to use because it's not like you're measuring exactly 50 milliliters in there. Just put a little bit of water in there, swirl, 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 get that baby to dissolve. And then you add the rest of the water to the desired volume, which is that etched line right there. And then you're going to continue to swirl. Because if you add water up to the neck right here, how much swirl room do you have? Not much, right? So you need to add about halfway first, swirl, 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 then add your desired volume. And then you're going to invert it to mix it. Now, we're not putting our fingers on top of these anymore. We're going to start using acids and bases and things that would affect your skin. So we're going to put either a cap on it, I do have some that have caps, or just parafilm. What's parafilm? It's like plastic wrap. It's like stretchy, non-polar plastic wrap. I have it in the back. So that's how you'll make a solution from powder to solution. You're done. How would you do this same process modified one step if you had to do it from solution stock, from like, a stock solution to a new diluted version?
You just have to use dilution equation to figure out how much water you need to add and use that much water.
No. Don't add water to my stock because then my stock's gone. Right?
Take out a little bit of stock and then do it.
Thank you. Okay, so the very first step here will be to take out, do you see my picture here? Stock solution. And in your calculation of M1V1 equals M2V2, you calculate one of the volumes. You're like, oh, I only need 1 milliliter of stock solution to make my new diluted solution. So this 1 milliliter of stock you pull out with what? It's on the board. Syringe thing, it's name. What's the name of that? Graduated pipette. And I don't care if you spell pipette with 1 P's and 1 T or 1 P. 2 T's, I don't care. Okay, so you'll use a graduated pipette, attain the volume you need, and then pop it into your volumetric flask, and then what would you do? Add water, invert to mix, swirl. So that's it, guys. I'm gonna stop for now. I have about 3 minutes left. I'll leave these pictures for you. We're not going to do that elaborate, and that's okay. Okay. So what I would do is maybe, with the molarity concept, what's for homework? Oh, what's for homework? It says molarity concept. Is it okay that I'm making optional? Like, I don't want to jip you of your education.
Oh, no, that's okay.
I'm not saying like, but if you truly understand it, and you can look at a problem and kind of understand it, do it, I'm fine with that. But I'm leaving it optional, that way you can use it for study of this as well. You have to watch the first 8 minutes of this video, because I had a 22-minute video for you to watch. What I've been doing is creating videos that cover some basic understanding of what you should remember from Honors Chem. That's why I'm not assuming that you remember everything from Honors Chem. I'm assuming a little bit when you have a video as a general reminder, and we'll actually use it a lot the following day. So where would you find the video? You would find it under, not the crisis. My computer's moving really slow, guys. I'm just going to show you as you kind of, if you're packing up, that's fine. I'm just going to show you. Let me go to my website. Huh? Yeah, so what I need from you is your active, I need your active reading guides, and I need your organic ones on your other packet. Is anybody going to do organic video tonight? Organic 2? All right. Hold on to your organic. I'll look at organic tomorrow, or if you know you're not going to use it tonight, pop it in the box for me. But I need your active reading guides, so drop them on the desk over here. That's fine. Huh? Yeah. Do not pull it out. Yeah. Give me the whole book. I'm trying to. Yeah. Do not rip your pages out of your book. If you didn't slap your paper, that's fine. You just need to drop it for me. I'm showing you where this video is, so look up here for me. Generally, I have the entire unit of study up. I have not had time to update my AP website, but it says complete molarity. I'm scratching that. Do as much as you need to for your own success. That means be driven to do something to make you successful if you need it. Organic 2 notes and 3, those are due later. I currently have, you can either put it in the box or put it at this table, it's fine. I currently have that due at the end of this week. You need to talk to me over the course of the next 3 days. If you don't talk to me, it's saying due on Friday, but you've got to give me some feedback. And then watch the first 8.5 minutes of introduction to basic chemical reactions, because tomorrow we are starting a pre-lab that requires you to understand this content. And I'll tell you doing your pre-lab in pairs. So if you want to go and claim somebody. Look, there's us, guys. Okay.
48.
It's your, how much of it are you watching? 8.5 minutes. Thank you. What do you have to do for test corrections? Good question. What do you have to do for test corrections? you have to, for multiple choice, write one sentence with encompassing the question and the answer in a correct way. For free response, you must simply write in a different color, pen or a different color or something, and either just correct minor mistakes, find the correct answer. If it's 100% like you didn't do the problem, you got to do the problem. That's it. Different color, do it. Correct it, whatever it is that you've got to do. Okay, thank you. Bye guys, have a great third and fourth, and teal. Sorry I talked to you the whole day. I'd rather do that than work you out and make you do more homework.
I'm lost.
So tomorrow you're preparing for that? I'm kidding.
I'm a woman anyway, so I might drag you back.
Alright, somebody update Courtney for me. You got hers? Okay. Did you get papers for all of her? Okay, all of her. Papers for her. Okay.
What?
I'm gonna pause this video. So it's not recording.